Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss the concept of local coefficient of drag and average coefficient of drag. So first we'll discuss the first one, the local coefficient of drag. This is actually denoted by CD star. The first point, the local coefficient of drag is denoted by CD star, and it is actually defined as the ratio of, we can say, this is defined as the ratio of shear stress. Shear stress, which is, we know that tau naught, it is the ratio of shear stress to the quantity of half into rho u square. Actually, this quantity is nothing but this is called dynamic pressure. This is called dynamic pressure, or we can say also know, we can say this is a velocity pressure. So dynamic pressure or velocity pressure, what it's called, this is the pressure actually which is exerted by a fluid. This is the pressure which is exerted by a fluid. You can say, you can write this, the pressure which is exerted by a fluid. Okay, and when this fluid will be exerted by the fluid, when it will be in the motion, when the fluid will be in the motion, and also you can say can be it's defined as the kinetic energy per unit volume. We can say also that is the kinetic energy, okay, per unit volume, okay, unit volume of fluid. Anyway, so this is about the local coefficient of drag, and this is the ratio. This is the ratio of shear stress. Okay, now when we are going to use this concept of local coefficient of drag, so let me write down this one. We can write this is CD star. So this CD star, or we can say this is also can be written in terms of CFX, CFX or CD star. Both can be mentioned, CFX or CD star. This can be written in terms of, as I told you, the ratio of shear stress to the quantity of half into rho u square, or this is the dynamic pressure, as I told you. Also, this local coefficient of, or you can say the local coefficient of drag, or also this is this term actually also called as, this is skin coefficient or skin friction coefficient. This is also called as skin friction coefficient. Okay, so this is the formula for this. And when we are going to discuss about this, suppose when you are going to use this concept, now suppose to determine the drag force, of what? To determine the drag force of on a surface, on a small strip, or you can say, suppose this is the small plate is there, and somewhere we need to consider a small strip, okay, which is a, suppose we can consider a small length, this is delta x or dx we can consider, and there will be a fluid flow will be there, and due to this fluid flow somewhere we will get the drag force. Okay, so in this condition, to calculate the drag force on a small strip of a length, okay, over the surface, so to calculate this drag force we will use this one. Okay, now this local coefficient of drag also, it quantifies the shear stress at a specific, or you can say at a particular point, or a specific point on a surface, okay, due to the fluid flow. So what we are going to identify, the shear stress. If you calculate the shear stress, also we are going to calculate the local coefficient of drag, CD star. Okay, and for that we need to calculate this value. So what is this value? The dynamic pressure, how will be calculated? Your velocity will be given and your density will be given. Density of the fluid will be known also. So for that purpose we can calculate the local coefficient of drag. This is also, we can say, as I told you, this equation can be also written for the laminar flow. If I consider the laminar fluid flow, for this, for a smooth flat plate, okay, okay, the local coefficient of drag, this local coefficient of drag can be written in terms of that CFX, that this one, the local coefficient of drag, or CD star, can be written the value actually. This is 0.664 divided by Reynolds number. This is nothing but REX. So this is also like, for the laminar. So REX is nothing but, we know that for a flat plate, we know how to calculate the Reynolds number, or how to calculate the laminar zone, like up to a distance X will be there, then boundary layer flow will be there. Okay, the boundary layer, this concept will be there. That means we have discussed already this concept in the previously. Suppose this is the plate is there and there is a distance of X, and the value of Reynolds number is 5 into 10 to the power 5. Okay, and we need to calculate up to what is the length X value. Anyway, this is for the local coefficient of drag. This is one concept. The second one, as I told you, that is average coefficient of drag. The second one is average coefficient of drag, and that is denoted by CD. This is denoted by CD, average coefficient, and it is defined as the ratio of total drag force. It is ratio of, we can write, it is defined as the ratio of total, this is the ratio of total drag force, to the, again same quantity need to be considered, to the quantity, the drag dynamic pressure, to the quantity, and the same, like what I told you, the dynamic pressure need to be considered here, but here we need to, one more area need to be multiplied here. Only apart from this half rho u square, we need to consider the A. Why we consider the A point, I'll tell you that one. At this point, as I told you, only we are focusing on a specific point. We are focusing on a specific point. Okay, at a small area or small zone, we are considering a specific zone. But here, if you consider this average coefficient of drag, here we need to consider the average of the local drag coefficient that need to be considered for the entire surface area. Okay, so this is, we can say, this is, it is the average. You can say this is the average of local drag coefficient. We can say average of local drag coefficient of over the entire surface, over the, you can say, the entire surface. The total plate, if you consider the whole plate over this one, we need to consider this. So how to write this one? This one we can write actually, as I told you, the ratio of drag force to the quantity of this. Also this one we can write CD equal to, this is FD, total drag force FD, divided by the quantity half into rho A u square. This is the one formula. Also we can write in other forms, like, see here the parameters what we have considered here. This is drag force, this is density, this is area. So these things we know, so no need to like mention these things. Area, and this is u, we know that free stream velocity. This is, free stream velocity, and rho is the density. Rho is the density of fluid. Okay, this is one formula. Along with that, also you can write this CD. Actually, this one also you can write CD equal to, also you can write this is 2 into CFX, or we can write 2 into CD star, like what we got previously, CD star. CFX and CD star is same, that's why you can write in this way also. And from this, if you write this equation, then from here we can find out CD equal to 1.328 divided by root over of REL. Now here, what is this term? This is actually the laminar flow. This equation actually we are considering for the laminar fluid flow. Laminar flow over a flat plate, over a flat plate. Okay, so this is the conditions, or you can say this is the definitions of local coefficient of drag and average coefficient of drag. So what is the purpose of these two concepts? Now, to find out the drag force, see, for this one is actually we are going to use this one. This one we are going to use the total drag force. We are going to calculate the total drag force for the entire surface, or for the entire object, you can say, for the entire surface, for the, or of the entire object. But here we need to calculate the drag force for a specific point. Okay, or you can say what is the shear stress is there at a specific point, we can calculate that. So this is the two difference of this local coefficient of drag and average coefficient of drag. So I hope you understand this theory, small concept of this theory. Still, if you are having doubt regarding this, you can give a comment on the comment box. Thank you all.